Welcome to Tollefson Physics. So what we're going to talk a little bit about today is this idea of work. So what exactly is work? Well, work is a transfer of energy process. So when you are analyzing a system for energy, you get to decide what objects do you want to look at. And if any of that energy is transferred to or from outside what you're looking at, it's simply called work. So work is simply a transfer of energy. And so we're going to use that to be able to figure out some things that are going on. Sometimes using work is easier than using items such as kinetic energy or gravitational potential energy, or maybe it's chemical energy that you don't know how to calculate or do something of that nature. And so we're going to use that. So keep in mind what work is it's a change of energy in any given system. And so when we think about conservation of energy, we can actually think about it in conjunction with work. So all initial energy plus work you put into the system, and if it's going out, that becomes a negative, equals all of the energy at the end of the day, at the end of the process, right? So this is conservation of energy in action. So it depends upon how I define my system. And so let's look at this process that I've drawn up here. It's just simple. I'm going to push this block with 2 newtons of force for 10 meters. Okay. So what's going on in that particular process? Well, this is starting, and I could go ahead, probably a good idea to always draw a LOL diagram, LOL, right? And so I'm just going to look at the block. I'm going to look at the block. And so if this thing's not moving to start with, which let's go there. It's not moving, it's not changing height, it has no spring, so there's no initial energy. Well, what about the final energy? What's the energy going to be at the end of this process? Well, it's going to be moving because I'm pushing it with a certain force. So I will have kinetic energy, and the only way that's going to happen is I'm doing work on the system. So then when I think about my conservation of energy equation, I'm going to have no initial energy because there's nothing going on. I'm going to add work, and that will equal the kinetic energy. All right, so what we have going on here is work is that transfer of energy from, say, my hand. Hand's not part of the system. And I really don't know much about my hand. I don't know like the chemical energy behind what my hand's doing or anything like that. But I could use a force gauge to figure out what force I'm pushing with. And so another way to calculate work is force times the distance. And look at this. I have the force and I have the distance, so I'm going to be able to do that in this particular case. And that will end up equaling the kinetic energy, which kinetic energy is 1/2 the mass times the velocity squared. So based upon this particular information, I can calculate the velocity of that block at the end of the push, and I'm assuming there's no friction. Now if there's friction, then my net force would be different, and that would change what the velocity is. But in this case, the net force will just have a pushing force of 2 newtons. And so let's go ahead and solve for velocity. It's always a good idea to solve for the variable first. So velocity squared equals force times the distance. The 2 comes on top, and the mass goes on the bottom. And so then velocity equals the square root of all that. And so then using conservation of energy, I can now figure this out. So 2 times 2 newtons times 10 meters divided by 5 kilograms, and then I got to take the square root of that. So 10 times, well, yeah, 10 times, well, let's do 10 times divided by 5. That's 2. So 2 times 2 times 2 is 8. So the velocity is the square root of 8. And that'd be meters per second on the outside of that. So a couple things to remember. Work is a transfer of energy. It is energy. It is measured in joules. It is calculatable using force times the distance. And so it's a transfer, in this example, it was a transfer of energy into the system, but it can also be a transfer of energy out, such as friction. Friction could pull energy out of the system, and therefore then you would have a negative amount of work. All right, so the only way to learn physics is by doing physics. And so let's do this problem. We have a 10 kilogram block that is already sliding on a surface that has friction. And so the friction, it applied to the block is 2 newtons. And we see that it takes 5 meters for it to stop. So the question I have for you to solve is how much work is friction doing on the block system? So solve that now, hit pause, and unpause when you're ready to see the solution. So here's the solution. So work is the force that's in the direction of the displacement. And so force parallel times distance is one way to write that. And so we have a 2 Newton force, and it traveled 5 meters. And so that's 10 Newton meters, which is the same as 10 joules. Remember, work is energy. So now let's take this one step further, and let's figure out how fast was the block going initially. So we're going to take that information, the work, and figure this out. So the first thing I want you to do is to create an energy bar chart or an LOL diagram. Hit pause when you're done with the diagram, unpause to see what the diagram looks like. Okay, so here's what the diagram looks like. So on the Earth block system, I have initially it's moving, and then friction causes it to slow down. And so the way that I've written that here is I am going to look at just the block, and the block is moving, so that's kinetic energy at the beginning, and it stops at the end. So I have no energy at the end, so the energy has to go somewhere. Well, it went into the friction. That's the work that was being done on the system. And the surfaces between the block and the surface warm up. They might deform a little bit, and so that's where the energy is being transferred to. So now use this diagram to come up with an energy conservation equation that will allow you to solve for the initial speed. Hit pause now and unpause when you're ready to see the solution. Alright, so in this particular case, the work is being taken out of the system. So I'm going to take that initial energy, which is kinetic energy, and I end up subtracting work because it's leaving the system. Because ultimately, I have no energy in the system because it's not changing height, there's no spring, and it's not moving at the end. So when I do that, then essentially what I'm saying is the amount of initial kinetic energy does equal the work that is being done because of friction. Once you know that, you can substitute 1/2 mv squared in for the kinetic energy, and then ultimately solve for the velocity as shown here. You should end up with a final solution where the initial velocity was 2 meters per second. So keep working on these problems so that you can improve.